Let me record this. So we have discussed about electrochemical. We have discussed about electrochemical last week, as well as on the some examples of advanced electrochemical prototypes on biosensors. And I also presented to you some market study of biosensors. Yeah. So this is another transducer that you can use to develop biosensors or chemical sensors. And also, interestingly, optical can also be used for physical sensors. Right. So this is just an academic interpretation of optical biosensors. Okay, it's not really important for you to remember, but at least you have some ideas on when we talk about biosensors. Okay, optical biosensors, it involves light, right? So optical means light. So we play with light. So I hope that because I think majority of you in the atomic spectroscopy class, so at least you are well versed in UV visible fundamental as well as fluorescence. Yeah, because these two are very important in when we are developing optical sensors, optical or chemical, optical biosensors or optical chemical sensors. They are very important. So we have to be well versed in UV, ultraviolet visible spectrophotometer, as well as spectrofluorometer. Okay, so those are instruments that usually used in optical biosensors or chemical sensors development, right? So there are other things as well, okay? So here, among the, when we say optical technique, apart from the UV, apart from the visible spectrophotometer or fluorescent spectrophotometer, this one also considered under optical, yeah? SPR stands for surface plasma resonance or surface plasma resonance. Okay, I'm not really familiar. I know the technique, but I haven't done any work on SPR. But then fundamental, I can explain to you what is the fundamental. We can also work with optical instruments, just I mentioned just now, fluorescence, UV, and then we also can use Raman scattering. This also, I haven't done any work on this, so it's quite difficult for me to explain. Okay, so I didn't include anything on Raman scattering, but there's a lot of research paper on development of optical sensor based on Raman scattering. Okay, and photonic. Okay, again, this is another that falls under optical biosensors or chemical sensors, but this is also beyond my expertise. So there are some researchers who do photonic in UPM, okay, but they are at engineering. Okay, so it's very interesting to use photonic, to work with photonic. Okay, so another aspect of biosensor, optical, when we talk about optical, okay, we are talking about naked eye detection, means that we can look at it. So it is based on color change. So colorimetric, okay, colorimetric means that the interaction of the analytes and the biomarker are translated into color change. So that is called colorimetric. So this is, of course, the simplest example where you use strip to detect the interaction between analytes and the antigen and antibody interaction. So you can see the color change on the strips. So there is one type of optical technique, colorimetric. Or you can also use what we ELISA plates, or small vials where you observe color change. Okay, so it can be also quantitative. You can see that it can be also quantitative. It does not have to be always qualitative when we talk about color change. The intensity of the color can represent, the intensity of the color change can represent the concentration of the analyte that we are measuring. Okay, so there are a few types, there are a few mechanisms that we can identify or quantify. We can use intensity, okay, we can use color base, the what we call as the color change in terms of how light, how dark the color change is. So that's how we can quantify the colorimetric based optical sensor. So one part, because optical is quite not so many in terms of fundamental, because the fundamental you learn in molecular spectroscopy, in atomic spectroscopy. As I mentioned, you should know by now about the UV visible spectrophotometer as well as fluorescence spectrophotometer. So that is the fundamental. Yeah, that is the fundamental. So for electrochemistry, I have to add some fundamentals on the electrochemistry. But for optical, you have to refer back to the notes that you have discussed, or lecture notes that you have discussed in molecular spectroscopy as well as atomic spectroscopy. Okay, right. Apart from this one, because this, okay, these utilize metal nanoparticles. In this case, utilize gold nanoparticles, sometimes silver nanoparticles. Okay, so one thing about colorimetric, it has to be really optimized to make sure that it can detect a very low concentration. Yeah, so you can see here, okay, if we are using if we are just using normal paper-based colorimetric, paper-based, okay, the strip is called paper-based. It's not that sensitive. It's not that sensitive. It requires a lot of the analyte. So if you are detecting bacteria or you're detecting protein, it requires a lot. If you are detecting a virus, then you need a lot of viral loads, a very high viral load in order to be detected. But we can change that, okay, with certain mechanisms. So just like here, we can couple the color change of the nanoparticle with some enzymatic, okay, reaction. Okay, don't worry about this. Okay, but I'm telling you that we can change the colorimetric that is not really sensitive into a very sensitive technique. Okay, so this one, it is called plasmonic ELISA. Okay, we know some of you might know the technique ELISA. ELISA is immunoassay, when you need to use antibody-antigen interaction, you want to quantify, or you want to test whether the antibody is specific towards the antigen. But this one, it is what we call as it's not twisted. The researcher changed something. It is called plasmonic ELISA. So instead of so why it is called plasmonic? Because it is the color change. The color change can be tuned so that you can observe blue color is positive, whereas red color is negative. And it can be quantified. And even you can see that the concentration, the sensitivity is very low. Okay, we can achieve down to picomolar. Okay, you don't have to use any sophisticated gadget. But with this mechanism, we can have naked eye detection based on color, and we can achieve down to picomolar. Yeah, so that's something that one thing about ELISA is because ELISA plates, okay, for those who know about ELISA, the plates has 96 well. Right? So you can imagine how many analyses that you can do, how many samples you can do at one go, because it has 96 well. So if we can have this, okay, it's very convenient to do a lot of analysis at one time. So another interesting about optical is the development of the material itself. Okay, because when we talk about optical technique, okay, as you may have discussed in your molecular spectroscopy or probably in your atomic spectroscopy, the material itself must be active in UV region, visible region, or fluorescent region. Yeah. So that one is a must. Okay, if it is not active in the optical region, then it cannot be used as optical sensor in optical sensor development. So there are many researchers, there are many research going on right now, and they are currently developing a lot of what we call as optical material. For example, here you can see it is quantum dots. So quantum dots is a combination of metals, okay? And then when we produce quantum dots in smaller size, you can see that they absorb different wavelength. Okay, I'm sure that you have understood the word wavelength, and under certain wavelength, okay, they produce different colors. Yeah. So by using this characteristic, we can actually utilize the wavelength, and when they interact with the virus, probably with the bacteria, there will be a color change. Okay, but the color change depends. If it is like here, you can view in visible region. That's why you can observe the color without any lights, UV lights. But this one is fluorescent, so it can only be observed under fluorescence condition. Means that you cannot just use normal light. You have to use UV lamp to observe these fluorescent properties. Yeah? But the fact that, as I mentioned in atomic spectroscopy class, that fluorescent is much more sensitive and much more selective. Yeah. So that's one thing. If you're interested in fluorescent, in the optical biosensor, now people are moving towards fluorescent. Yeah. So this one is also a paper-based biosensor, just like the one that I mentioned, the one that I showed just now. But the commonly used gold nanoparticles. So it shows color, orange color, or dark purple color. But we can also use quantum dots, okay, as the instead of gold nanoparticles, and it has been proven that under UV lights, okay, this is under normal lights. Under UV lights, you can observe the appearance of the quantum dots on the papers. Yeah? So it can be also utilized in a solution form, as well as it can be on top of paper-based sensor. So as I mentioned, of course, by using fluorescence technique, it actually lower down the sensitivity. Means that you can detect much less concentration compared to the UV and visible region. Okay, so the most important part in UV, sorry, in development of chemical sensor or biosensor is miniaturization. Means you make things smaller. Okay, so we need to make things smaller. So that's why, okay, the smaller the device is, okay, the easier for you to change it into prototype for commercialization. So miniaturization is a must. So we can make it things small. So this one, I think you have gone through in atomic spectroscopy. We need to have a light source. This is the sample introduction, and this is the detector. Okay. So instead of using what we call a solution, you are probably used to using cuvette to analyze solution. We can also change it into solid. Okay, so if you look at here, you see the setup is the parts, the light source, the detector, and the samples. They are separated. They are not in the same one big instrument. You can detach them. You can make it. You can attach them in different ways. So you can see that this is the light source, right? And this is the detector. So if you choose to do solution based, then you can see this is the sample holder. Okay, you need to cover up this one because of the stray light effect. So you can see now instruments are getting smaller and easier to handle. And of course, it is actually much cheaper compared to the bulky instruments. Yeah. So instead of using solution, okay, you can also make it into a solid form. Yeah. Okay. So this one, we can immobilize DNA, antibody or enzyme on top of a solid support. Okay, and then you can also use chemical reagents. Yeah, for example, if you want to detect heavy metals, you can put on top of the solid support for the with the chemical agents that are going to respond to the heavy metals, for example. And then you can see here, instead of using, if you have the capacity to look at UV instrument, normal UV instrument, you see that there are lights shown and so on. But instead of lights shown in an empty space, or we can use optical fiber. So this one is a fiber. Yeah. So the light is moving in the fiber. So with this technique, you can actually make it portable because the fiber can be detached, it can be connected back. So this one, it is a much simpler setup. Okay, so fiber. Okay, so this one, okay, is what we call as optical fiber. So you can detach it, then attach it back. So it's quite portable. Yeah, right. If you have questions, just stop me. All right. So this is way to go for miniaturization, and I've done this many years ago. So I'm sure now the advancements is much much better than this. Yeah. Okay. Right. Okay. So on top of the fiber, just like on top of electrode, you can put the reagent, you can put the DNA, you can put biomarkers, enzyme, and then when you have the metals interacting with the reagent, or you have the virus or the bacteria interacting with the biomarkers, then the optical fiber, okay, can will have a change in terms of light properties, and that changes can be detected by the detector, because we have one part as a detector. So this is mainly the mechanism of optical sensor. You have interaction of analyte with the reagent on top of the optical fiber, and then changes in the signal will be detected by the detector. Yeah. All right, sorry, just move on. Okay, surface plasma resonance. Okay, this one, as I mentioned, it is based on light, and this is a very sensitive technique because it is quite expensive. Okay, depends on the brand as well. So you can see that instead of just now we talk about intensity, we talk about wavelength, right? The optical properties of the lights, but surface plasma resonance, they use refractive index. Okay, refractive index in terms of angle. Okay, so these are, if like this is the antibody, okay, that is immobilized on the SPR surface, okay, usually is gold, okay, gold chip, okay, and then let's say you just flash through samples, right? And then if there is antigen that is interacting with the antibody, if there is, yeah, there will be changes in terms of the angle of refractive index just now. Okay, so you can see that one is before any interaction with the analyte, okay, virus or DNA or bacteria, and then the number two, you observe changes in terms of angle when it is exposed to the sample. Okay, and then if the sample is positive, there'll be changes in terms of theta. This is called theta, angle of the refractive index, how much it is being reflected. Yeah? So this is very sensitive technique, as I mentioned, but depends on the brand. Okay, and usually being used to confirm that the biomarker that we develop is selective. Okay, so we use SPR technique. At this moment, I haven't come across SPR being miniaturized. Mean it is converted into a small device. Probably I haven't come across. All right, this is the fundamental of SPR, but as I mentioned, it is based on refractive index. The changes can be measured as a change in the angle of incidence or a shift in the wavelength of light absorbed, and can be measured as change in the SPR surface plasma resonance signal. Okay, so this is again the same principle of SPR. Okay, so now this is photonic. Okay, I believe that it has been used in probably more advanced sensors, but I don't know. But you can see that photonics, when we talk about photonic, we depend, you can see the light shown. Okay, there is an implant inside, there is an implant inside the body. Which is, so the implant probably has contained, you can see here, okay, contain certain markers, biomarkers or chemical markers, okay. So when there is an interaction between whatever that we want to detect inside our body, and it interacted with the markers here, probably biomarkers or chemical markers. Probably there is no markers at all. It may be just material that is responsive to the analytes of interest. And then when the light is shown, okay, so there is changes in terms of, just like before, probably there are some characteristic of the lights. Characteristic of the lights has changed. And of course, people have done some analysis before that the characteristic change is due to the interaction with the analyte of interest. So this is, of course, a very sensitive technique, but a lot of work has to be done before we can come up with this optical sensor based on this photonic. Yeah? Okay. As I mentioned just now, that in order for us to come up with optical sensors, we need to have compounds, we need to have materials that is active in UV or visible or fluorescent. So just now I have shared with you one which is quantum dots. Okay. We also have like dye, okay, but dye, I may say that dye is history. I'm not saying that people don't use dye anymore. Dye because of the color change, yeah? But using quantum dots, because you can have a much better response, a much sensitive response. So that is why we are moving toward nanomaterials, okay, and fluorescent materials. Okay, so this is called fluorophore. This is called molecular beacon. Okay, and then it is attached with fluorophore. So fluorophore means that chemical reagent that is active in fluorescent. Yeah, so you can see what is the mechanism of molecular beacons. All right. And I hope by now that you are familiar with this ATCG. Yeah. So you can see that molecular beacons, how do we specify this molecular beacon is the shape of it's not DNA, is what we call as nucleic acid or peptide, series of nucleic acid in a form of this is the structure. So this is what we call as molecular beacons. Yeah. So you can see you have round shapes, and one end of this DNA is attached with fluorophore. And also we have fluorophore here. So CY3, CY5 is fluorophore. Okay. So let's say if this molecular beacon is exposed, yeah, to samples that contain DNA here, a series of DNA of interest of the target that you want to analyze. So what happened is the shape of the molecular beacon, instead of remaining as the round shape and this shape, it will spring open. It will automatically open because the reaction between ATCG. So you can see that from this shape of molecular beacon, it's open up, okay? And then there are changes in terms of fluorescence, okay? Why? Because we have fluorophore, and then I believe that you know about fluorescent, okay? The thing about this is what we call as FRET, fluorescence, resonance, energy transfer. So this one, we have not discussed anything in atomic spectroscopy because it's quite advanced. So what you need to know is if this fluorophore is close to each other, okay? If this fluorophore is close to each other, one is a donor, one is an acceptor, you may observe energy transfer, and then this energy transfer can be observed in fluorescent spectrum. Yeah, but if this molecular beacon find the target DNA, yeah, find the target DNA, this structure will be destroyed. You can see that it goes like into chain structure. So the fluorophore here, CY3 and CY5, will be far away from each other. So when they are far away from each other, there will be no more what we call as FRET signal. Yeah, there will be no more of FRET signal. This also can be observed in the fluorescent spectrum. So that is how molecular beacon is used, and molecular beacon is also one of the active material being used in development of optical sensors. Okay, a gold nanoparticle is quite common, so I don't want to discuss this. Also, silver nanoparticles is being used as an active material for a visible region, because it is color based. It is called colorimetric. So you can see that the wavelength is in the region of visible. Okay, so carbon dots. Okay, I have shown you the picture of carbon dots for those of you who has taken atomic spectroscopy. So carbon dots is quite similar in terms of color change in fluorescent region. Is quite similar to quantum dots, just like the pictures that I've shown at the earlier slide. And they're also what we call as graphene quantum dots. Means that the quantum dots can be prepared from graphene. Okay, so just now the quantum dots that I showed you at the earlier slides, it is based on metal oxide, combination of metals. But this one also we can use graphene to make it into quantum dots. So these are all materials that you can use to develop optical sensors because they are active. Because they are active in fluorescent regions. Of course, there are materials who are active in UV, in visible, but now in sensors, because of the sensitivity of fluorescence, so researchers now are moving to fluorescent material. Okay. This one, there are of course issues using optical sensors. Anything that interfere with lights, okay, can be a possible interfering compound or interfering substance. Anything that interfere with lights or anything interfere with colors will be an interfering substance. So this is an issue that we have to deal with. For example, if you have if you have to study a blood sample, so the blood is red, so we have to filter the blood, removing the red blood cell because we do not want the color of blood to interfere with the color change. Electrochemical as well has certain issues. Okay, electrochemical is due to current. So anything that interfere with current will have some contribution in terms of interferences. For example, if you want to do analysis of seawater, because seawater contain salts, is highly concentrated with salts. So when we use electrochemical sensors, it actually very difficult because the salts are interfering with the current. So that's why when we are developing sensors, we have to evaluate which one is the best, optical or electrochemical. So that's why we have to evaluate the situation first before we can use what are the transducers that is suitable. Okay, so that will be on the optical sensors. So not much, okay, that I can share, because if you are well versed in UV and visible spectrophotometry or fluorescent spectrophotometry, then that is good enough. The rest are just developing materials like quantum dots, carbon dots, fluorophores. Okay, so if you can do that, an active compound in fluorescence, then that's an advantage. So I'm going to share with you the last part of on my parts of for biosensors and chemical sensors is where to start and how to start, what to do first if you want to do this. Yeah? If you want to do biosensors, chemical sensors, what do you do, right? So this is generally what we do. First is to check the sensing principle. Okay, so we need to ask ourselves how is going to give signal. Okay, if the interactions will give signal. Okay, so if you are working on electrochemical sensors, do you have electrochemically active compound that will give out the signal, that will change according to the analyte change, for example? So if you're working with optical, do you have optically active compound that will change the signal once it interacts with the analyte? So this has to be answered first. Okay, this has to be answered, especially when you are working with biosensors. You have to check whether your biomarker is responsive, selective towards the analyte or the analyte that you want to measure. Okay, this has to be answered first. Now, for example, okay, the sensing principle of an optical sensor is based on shift in the characteristic optical signal, optical platform, or okay, result from interaction with analytes molecule. So this one, I'm just giving you an example of sensing principle. Yeah. So after you have like confirmed, yeah, the sensing principle, you are yes, you are confident that the sensing principle is correct. You have studied the fundamental, you have studied all the possible interference, especially, and you are, as I mentioned, confirm confidence that you can have a very good signal in future. So the one thing about biosensor is you do not want it to be too slow, because the purpose of having biosensor is for you to bring to the site, right? You want to detect and you want to have the results there and then. You want to have the results at the site. So you cannot be, you cannot have the response time probably 24 hours, 48 hours. So that defeats the purpose of developing biosensors or chemical sensors. Yeah. So what is response time? The biosensor response time is the time it takes for the sensor output to reach its new signal. Means that the interaction happen between the analyte and the marker. Okay. And it should be translated by transducer. Mean the change, the signal, the readout should be by the detector or by the transducer, and it is displayed. So if you have to wait for 24, 48 hours for the response to be observed, then it's not a good sensor, right? So response time is for the first thing that you study. So you do the reaction. If it is too long, the response time too long, then it is not going to be working. Yeah, it's not going to be practical for biosensors. Okay, and then after that, you have done some work, the groundwork. Then you think about you have to like study the material involved. For example, if you are developing quantum dots, if you are developing new compound for hybridization indicator, if you are developing a new marker, chemical marker, biomarker, a new chemical reagents. So those things has to be characterized or optimized. Yeah, means that you have to check how much the concentration that is suitable to put on top of the sensors. Okay, electrodes, optical fibers. You need to study how much. You cannot just put everything and then expect it's going to work. So there's a lot of study in terms of volumes, amounts that you need to put on top of the sensors. And we have discussed on immobilization chemistry, right? How to attach the biomarkers. That also has to be studied, okay? You have to choose the right technique of immobilization. Okay, the third one is once you have put the biomarkers or nanomaterials with the right amount, with the right chemistry, now you need to study the parameters according to the transducer. For example, if you're talking about electrochemical parameters, you have to study the potential, you have to study the scan rate, you have to study the supporting electrolyte, for example. Those are electrochemical parameters. If it is optical, you have to study the lambda, okay? You also have to study whatever that affecting the optical properties, okay? So these are the third one, okay, that we need to do in development of sensors. Okay, now let's say we have done all this. You have a very good reading, okay? You have a very good reading, okay? You're happy with it. We have to check whether the reading is reproducible. It means that if you do the same setup, the same setup, concentration, amount of biomarker, probably the same voltage, the same potential, or the same lambda, the same wavelength, you should by right getting the same signal, the same absorbance, the same emission, or the same current. So let's say if you do 10 sets of the same experiment, then by right you should have a good, more or less similar response. Yeah? So it cannot be a big difference. Today you get different reading, the next day you get different reading, then it's not going to work. The biosensor or the chemical sensor is not going to work if you have a non-reproducible signal or results. So this is a very important evaluation. You need to evaluate the reproducibility. Okay. And next one is, of course, you have to study in terms of selectivity. Okay. So possible interference. If you are studying metals in water, if it is in drinking water, if it is in tap water, you have to know what are other metals, what are other ions, what are other compounds that is in the water, commonly in the water, that will interfere. Okay, you need to study. If there is a possibility, the reading will be like haywire if you introduce the interference. Okay, so this one based on the the nature of the samples that you want to do. Okay, for example, if you want to study urine, you need to know what are other compounds, what are other chemical compounds or biochemical compounds that exist, naturally exist in urine, so that you have to test whether it is going to be affecting the reading or it's not, or minimum affecting the reading. Okay, so this one is actually a biggest challenge for us who are working in sensors. Okay, now you are good to go. So the last part, of course, we have to validate, yeah, your sensors. Okay, so validation with standard technique. Okay, usually we use real sample. Okay, so if you are to develop a glucose biosensor, of course you have to validate with standard technique of glucose detection. If you are developing a chemical sensor for detection of heavy metals, you validate with ICP, you validate with AAS. It means that the same sample, the same real sample, you run with your newly developed sensors, and at the same time, the same sample you run with ICP or AAS technique. And we look at the results, whether they match or not. Okay, so this is validation, yeah, called validation. And if you are to do quantitative analysis, there are, of course, extended works that you have to do, which is you have to really study the concentration, okay? We call it dynamic range, to get the linear parts. Okay? So, of course, once you get the linear part, well, the concentration means that which concentration that it is linear, okay? Because if you want to have the results to be quantitative, you cannot have a non-linear dynamic range. Yeah? If you study concentration, then if the concentration increase, then the current or the response also must be similar to the or responsive to the concentration. Yeah. So that's why when we do quantitative analysis, we have to really solve this issue, which is the concentration study, construct calibration plots, okay? And this is very challenging actually. And then identify the limit of detection. Means that how low the sensor can detect, how low the concentration of the analytes of interest, how low you can detect. And also, we have to test whether the calibration plot is good, okay, by introducing unknown sample types. Means that you probably can use real sample, or you can use spike sample. Spike usually we know, but it's best that you introduce an unknown sample. Together you validate certain techniques, and then you expose the unknown sample to the sensor that you have developed, and then do comparison in terms of concentration that you have gotten, okay? So this is very important, and all this actually takes a long time to develop, so it's not that easy. Okay, for qualitative analysis, just like you want to know yes or no, all right? You don't have to do calibration plots or dynamic range just now, but at least you have a very good reproducibility. Means that you have 10 different 10 similar sets of experiments. You should be getting more or less the same signal. And then when you calculate relative standard deviation, it should be below 5%. If it is like 10%, then it's hard to get a good sensor from that. And again, even though it's qualitative, you have to do real sample and validations. Yeah? Validation with the standard method. So this one is a must thing to be done in development of sensors. Another issue is the sample. Okay, so when you talk about real sample, okay, we can imagine the samples. If it is medical related, you can think about blood, urine, sputum. So it's not easy to work with real sample. And if it is industrial samples, you can imagine the waste from industry, from the paint industry, from the semiconductor industry. So how do you do that? Okay, you have to think about whether you need to come up with a pre-treatment. Okay, because the purpose of having biosensors or chemical sensors, again, we want to bring it to the site. Okay, so if the pre-treatment of the samples requires lab, then it's not going to work. Yeah, it's not going to be practical. You have to like bring the biosensors or the chemical sensors to the lab, do some pre-treatment first, and then test using the sensor. So in order to sell, okay, let's say you want to sell the sensors, you have to think about whether the pre-treatment can also be incorporated in the sensors. Same goes with purification of the samples. Sometimes some samples requires purification. Some samples requires pre-concentration. You need to pre-concentrate the sample. So this has to be think about before we can come up with a prototype. Okay, So when we start to think about prototype development, just now is the real samples issue, which I put in here. How are you going to introduce the sample? Is it by dropping? Is it by injecting, or is it just exposed to it? You just dip it inside the water, or you just dip inside the waste. You can, if you have like, you want to check pesticide level in veggies from Cameron Highlands, so you can just like, you have a sensors in the form of pen. You can just like stab the veggie, and then you can read the level of pesticide. Okay, so you have to think about this, whether it can be detected very easily. Okay, because lab work is not easy as the real world, of course. Okay, so miniaturization, of course, you have to make it compact, small, right? Packaging, of course. Why? Because you want people to like it, right? It has to be user friendly. The display is very user friendly. You don't want them to like has to think about how to interpret the results. No, you just want them to be in numbers, for example. Yeah? All right. Price must be competitive. So multiplex means that if there is a possibility that you can buy a sensor that can detect glucose, cholesterol, urea in just one go, in using one device, of course you will love that, rather than you have to buy the sensor separately, right? So this is called multiplex. Yeah, means that you have multiple sensors in one device. Huh? Robustness, okay? Robustness means that, okay, you don't want sensors that you need to keep inside the fridge. You want them to be out there. You can just put on table, you can just put in your car, whether the heat is very high, the temperature is very high, it's not going to affect the reading. So you need robustness, okay? And of course, software, because interface, yeah? Software, of course, is something that very important in development of sensors. You need to translate the spectrum, the current, whatsoever that you have gotten into a display that people can read, common people can read, okay? So you know, okay, if your glucose is 6.5, 5.2, so that is what people want, okay? So if I'm testing TB, so right away, the word positive means that, okay, it is TB positive. You don't want to, people don't want to interpret the results. They just want to know the diagnosis, okay? So let's say you're doing metal analysis, you just want, it is above safe level. So probably you put red, a red signal showing that it is way beyond the safe level, okay? So that's why software is very important for you to, for us, especially working in sensors, which is, you can see from here, there are many experts involved. Okay, for myself, I'm just focusing on the chemistry, all right, all those, the one that I have discussed, reproducibility, interference, but when it comes to translating the sensors into final product, then we have to think about all this. So Philips, okay, so everybody know Philips, that's why I choose Philips, where you use Philips, you have like air fryers, you have also vacuum cleaners, so all those electrical gadgets, you have probably using Philips. So Philips launches next generation wearable biosensors now. So they are also working with biosensors, particularly in medical diagnostic. Why? They are focusing on because we know infectious disease like COVID. Yeah, every time the frontliner or the medical workers has to gear up, has to suit up before they can approach the patient. So imagine that every time you have to suit up, so it's not comfortable at all. Okay, as well, the PPE is not comfortable. The personal protective equipment is not comfortable. So Philips has developed a biosensor called BX100, helps provide rapid development for clinical surveillance to help to reduce the exposure of health worker. Means that they come out with a device where they can put on the patient's body, so everything, at least some vital can be monitored outside the patient's room. Yeah, so you can see this is how, I don't know how they do it, because that is their business secret, but this is something that we want in future, so that any infectious disease, wearing the protective clothes, it is in fact very stressful, especially in warm countries. You have to wear all those PPE. So these are, if you can have some biosensors, wireless wearable biosensors, then it really helps. So that's it. Okay. Any questions? No, everybody is waiting for berbuka. All right, okay, it's okay, I understand. So the next one, as usual, we start at 8:15. Okay, we are going to discuss group assignment. Okay, similar to spectroscopy just last Wednesday. Okay, so I hope the group assignment will reduce your burden of a lot of assignments, I understand. Okay, so at least this one can help. Okay, so see you around 8:15, right?
Okay,
All right, right.